Hello, everyone, and welcome to this video on statistics. And this time we are going to discuss one of the most important statistics distributions known by the normal curve, sometimes known by the bell curve. And we are going to see that this distribution has really interesting features, and it is widely used in a lot of real-world applications, actually. Here is the story of this. When you collect data, it could be scores of tests of a large class. It could be ages of people, salaries of employees, and so forth. And then when you draw, let's say, the histogram, so you create your classes and you create the histogram of your data. If it turns out that this histogram has like a bell curve, somewhat symmetrical around an axis at the middle, then this is what we call the normal curve. Obviously, not every curve or not every distribution or not every collection of numbers will lead to a normal curve. We are going to see that we have actually different distributions. But if it turns out that the data that you collected, when you draw it, it shows like a bell curve, it shows like we call the normal curve, then trust me, you are going to be benefiting from a lot of laws or a lot of features in statistics about this curve, and you can infer or you can collect or find a lot of, I would say, information about your data, particularly about probabilities of things happening. Or if you, for example, if you are dealing with scores, you may have a question that says, I would like to know the probability of the students that are, let's say, scoring between this score and that score and so forth, or the probability of the students or the amount of students or the proportion of the students who scored bigger than let's say 75 and so forth. Well, as we talked before, statistics is not just about small set of data. Usually you use the tools of statistics because you have a large amount of data, you take a sample, and hopefully from that sample you can have some useful results obtained from it. Okay, well, what we're going to learn today, we are going to understand the properties of a normal distribution, and we are going to calculate what's called a z-score. We use that z-score to determine the area, which is actually a probability under the normal curve, the area under the normal curve. So people who did this before, when you say z-score, normal curve, they know what does it mean, the area under the normal curve. And this is what we'll be using or we'll be learning this time. And of course, like I said, the example before, if you would like to know how many people, the proportion of people, let's say, earning before this much, this salary and this salary, given that your curve, it's a normal curve. Now, if it happens that your distribution is not like a bell-shaped distribution, then of course you cannot use those features. You have to learn about that distribution. There are a lot of very well-known statistical distributions, but this time we'll focus on the normal curve. Well, here is something that is not bell curved. You may do your histogram, and your histogram looks like this. Of course, this is too perfect, but if overall your distribution looks like a rectangular distribution, that's what actually we call a rectangular distribution. Remember when we did the histograms, we did the classes and we did the frequency. So this is just like a rectangular distribution. So sometimes you may have a distribution like in this, like they call it G-shaped distributions. So this is not a normal distribution. So sometimes you may have what's called a bimodal distribution. Remember the mode? The mode is the piece of data that is occurring the most. So as you can see here, we have two modes, and this is called bimodal distribution. This is, again, not what we're going to be talking about. Skewed distributions, you may have, for example, most of the data here is to the right. We call this left skewed, and this is right skewed. Again, these are not normal distributions. Well, if you draw the curve, let's say you go from the center of each class, you draw the curve of skewed distribution, you may have something like this. So this is skewed to the right, and this is skewed to the left. But, this presentation is about the normal distribution, but it does not hurt if we talk a little bit about skewed distribution. If you have a skewed distribution to the left, skewed to the left distribution, uh, the mode again is the piece of information that appears the most. Obviously, this is the mode, right? If I go back to distribution, this is the mode, means that the highest histogram or the highest bar, that's called the mode. And a little bit to the to the left, you find the median and you find the mean. So if you have a skewed to the left distribution, these are again averages. These are measure of the center. You find that the mean is less than the median, less than mode. However, if the distribution that you are working with is skewed to the right, you will have the mode obviously as the tip of the distribution, and then a little bit to the right, you find the median, and then you find the mean. So as you can see here, the mean is bigger than the mode when you have skew to the right, and vice versa. But again, this is not my concern this time. We're going to be talking about what's called the normal distribution. And here it goes. Now, if you collect your data and you set the bars, you set the classes, and you do the frequency distribution, and if it turns out that your distribution has this look, it's like a bell curve, like an upside, kind of like upside down parabola. It looks like a bell curve. It has some symmetries. You see the mode here as the center, and then, and let me tell you something. When you collect data, the probability or the chance that you are going to hit a perfect normal distribution, forget about it. Life is different from theory, but sometimes people can allow themselves to use the laws of the normal distribution if the distribution looks somewhat like a bell curve. And then we can always justify these things. You say, well, it is almost a normal distribution, so I can use it. So sometimes called the Gaussian distribution. Gauss, it's a German mathematician who works a lot with these type of distributions. And the graph of a normal distribution is called like a normal distribution, sometimes called bell shape. It is symmetric about the mean. If you look at this one here, the mean and the mode and the median are the same. And that's what's good about the normal distribution. When we looked at the skewed distributions, the mean, the mode, they are different from each other. And the median, these three averages are different. But when you have a normal distribution, they all fall at the same place. As I just told you, the mean, the median, the mode of a normal distribution, they all have the same value. They occur at the center of this distribution, where the symmetry happens to happen. So if you have a normal distribution, then you have what's called 68, 95, and 99.7 rule. What does it say? It says approximately you have 68% of all the data. When I say data here, means 68% of the scores, 68% of the ages of the employees, 68% of the salaries of the employees, whatever data collected. If that data, when you draw it, it has a bell shape to it, then you can say you have approximately, of course, this is approximations, but a good approximation. You have 68% of all the scores, 68% of all the salaries, 68% of all the lies, they are within one standard deviation of the mean. Means once you calculate the mean, and we know how to calculate the mean, you just add up all the data, divide by how many of them, and we know how to calculate the standard deviation. So once you calculate the standard deviation, you have the mean. Let's say, suppose a hypothetically, just let's take a numerical example. Suppose that the mean is 5, just hypothetically, and the standard deviation is 1. So 5 is at the center. 5 plus 1 is 6. 5 minus 1 is 4. Means you have 68% of the ages, 68% of the scores are between 4 and 6, or the scores between 4 and 6. And you have 95% of all the data lies within 2 standard deviations of the mean. Means if you have the mean and you add 2 standard deviations, like for example 5, in the example I just gave you, the standard deviation is 1, the mean is 5, 5 plus 1 plus 1, which is 7, 5 minus 1, which is 3. So you have 95% of the data between 3 and 7. And almost all the data lies between 3 standard deviations of the mean. 99.7% of the data. Again, we cannot use these rules, or this was called 68, 95, 99.7 rule, unless the distribution we are working with is a normal distribution. Okay, now here is something that is really, really useful called the Z-score, or sometimes called the standard score. If I say, for example, I have a class, let's say I'm teaching class, I gave a test, the average score is, let's say 75. When I add up all the scores, I get 75. And then I have a person, one of the students in my class scored 86. So is 86 good, bad? Well, definitely it's a good score, it's above the average. But if you want to have a really good measure, if you have a really good idea about the position of the score among scores, you need to find out how far it is from the mean. As you can see here, well, we are going to use the standard deviation. Because the standard deviation is the piece is the statistics that will measure the dispersion. It will measure the, I would say, how the data is spread out. Because you can have two classes with the same average, which is 75. But one class, one section, the students, they score around 75, some of them are 73, 81, and so forth. So the majority of the students, they score around 75. So when we did the average, we obtained 75. And then we may have another class where the mean is 75, but the score is so spread out. We have very low scores and we have high scores. But when we did the average, it turns out to be 75. So can we say that these two classes, for example, if someone scored 87 in both, or 86 in both of the classes, two people scored 87 and 87. Well, the one who scored 87 in section one, kind of like, well, it's not really, it's among the other scores that are around 75. But the other 87, it's a little bit, it's far away as far as how many standard deviations, because you have a large standard deviation. So we are going to use what's called the Z-score. The Z-score will tell us how far away that piece of data, that age, that score, that salary is far away from the how many standard deviations it is far away from the center, from the mean. Here is another example where Z-scores are very useful. If I ask you, who is a better athlete, Phelps, the swimmer Phelps, or Michael Jordan, the basketball player? Michael Phelps or Michael Jordan? Well, you may say, well, this is swimming and the other air basketball. I cannot compare them. Well, suppose that these two guys are, we need to pick one for, let's say an award or something given by the White House, and, you know. But of course, apparently you may say we cannot compare them because these are two different things. But we are going to look at how good Phelps is compared to the other swimmers and how good Michael Jordan is compared to the other basketball players. And we are going to, for example, find a group of swimmers, let's say average the performance, let's say some time of doing, let's say 400 meters, like say freestyle or whatever type of swimming. We get the standard deviation and we get the time of Michael Phelps and we compute his Z-scores. Then we do the same thing for basketball and we compute the Z-score of Michael Jordan. So the person with the higher Z-score is the person who deserves the award, because that person is scored way above or way above the rest of the other competitors or the other, let's say, swimmers or basketball players. Another example would be, well, suppose you have, for example, you have two students. We would like to award a scholarship. Two students. One student scored 75 in a math class, and another student scored 93 in a, let's say, in a music class. Well, you may say, well, I cannot compare these two. Math is not music. So, but we're going to compare the Z-scores. We'll compute the Z-scores of both students, and then the person with the higher Z-score is the person who deserves the award. But again, we are going to focus more on just one type of, one thing. And here's the formula to compute the Z-score. So the Z-score is the value, the score of the test, the time of whatever you collecting, the salary of an employee minus the mean, minus that X bar divided by the standard deviation. So this is, if you are asked to compute the Z-score of something, of a piece of data, that's how you do it. So let's take an example. Suppose you have a normal distribution. By the way, when you the z-score is not related to normal distribution. So you can compute the z-score for any type of distributions. Just give me the mean, give me the standard deviation, and give me the piece of data for which you want to compute the z-score, and I'll do that. But suppose that now we have a normal distribution of mean 60. All what matters of us now is just the mean, which is 60. The standard deviation is 15. So let's compute the z-scores of the following values. What is the z-score of 75? 75 minus 60 divided by 15 is the z-score of 75. The z-score of 81 is what? Is 81 minus 60 divided by 15. What is the z-score of 60? Is 60 minus 60 over 15, which is 0. 33 minus 60 over 15. That's the z-score of 33. So the z-score can be positive, can be negative, can be 0. So here's the 75. 75 minus 60, which is 15 over 15, is 1. Means that 75 is 1 standard deviation away from the mean. Away here above, of course, when the z-score is positive, the piece of data is above, is bigger than the mean. 81 will do the same thing. 81 minus 60 over 15, which is 21 over 15, 1.4. So it means that 81 is 1.4 standard deviations above the mean, away from the mean. Let's go back now to 60. We say 60 has a z-score of 0, and 31 has a z-score of negative 1.8. What does this mean again? Is that this 33, suppose that this is a score of a test of a student, we're going to say that this student scored 1.8 standard deviation below the mean. Is that good or bad? Well, it depends on the context in which you are doing this. Now we are going to hit one of the most important things of the normal distribution. Now we're going to focus on the normal distribution. We are going to talk about the percent of data, the probability, the proportion of data between two values. The best way here is to draw a normal distribution just by hand and then use a table. Well, this is kind of like outdated. So I'm not going to show you the table. Well, I'll show you the table. I'll show you how to use it, probably, maybe, but now we are in the era of technology, so you can use a calculator or you can use a website. Before I started doing this presentation, I just went to Google and put normal distribution probabilities, and I got a nice website that I'm going to share with you. You can use that to compute your percentages under the area under the normal distribution. So here it is. So when you draw the normal distribution, you draw your histogram of normal distribution, you can draw what's called the standard normal distribution, because 0 here is not always the mean, of course. This is what's called the standard normal distribution, because I can convert every normal distribution collected in real life, right, into what's called the standard normal distribution, where the mean is 0. This may sound a little bit confusing. You may say, oh, what are you talking about? Well, give me a minute, then I'll tell you what I'm really talking about. I think I need to go. Let's go directly to an example that will show you what I'm trying to say. Here is an example. And that example will clarify everything, actually. So here is what it says. Assume that the length of time for a horseback ride on the trail at Triple R Ranch is normally distributed, or it follows a normal distribution, or it has a bell curve with a mean of 3.2 and standard deviation 0.4. Every time they give you a normal distribution, they will give you two pieces of information. They will give you the mean and the standard deviation. So here, somebody collected some data, whatever, and came back to us and says, well, the length of time, the times of horseback collected, we did the histogram, looks like it's a normal distribution, the mean of 3.2 hours, and the standard deviation 0.4 hours. Now, what is the probability? What is the percent? What is the proportion of horseback rides that last at least 3.2 hours? We would like to have that at least 3.2 hours. Means what? 3.2 hours and up. Would like to know what is the percentage of horseback rides that are at least 3.2 hours. So what we're going to do here, we're going to compute the z-score. Well, you see, have you noticed that 3.2 hours is actually the mean? So I can say, well, the mean is at the center, right? At the center. So it means that we have 50% above the center and 50% less than center. So kind of like this is an easy exercise, right? But what happens if we say, what's the percent of horseback rides at least 2.8 or 2.9? Well, that's not the mean. So here in a normal distribution, half of the data is above the mean and half of the data is below. So he has 50% of horseback rides that are above 3.2 hours. And we have 50% of those times of horsebacks that are less than 3.2 hours. Well, here's another question. Well, this one is trickier than the first one. It says, what percent of horseback rides last less than 2.0 hours? So let's convert. So this is one way to do it. I'll show you a much easier way to do it. First of all, let me get the z-score of 2.8. So what is the z-score of 2.8? So I'm going to take 2.8 minus the mean, which is 3.2, divided by the standard deviation, which is 0.4. 2.8 minus 3.2. And this is the z-score that goes with 2.8. And then we are going to say, well, the area is, or the percentage is 15.87% or 0.1587. How did they get that? Well, they use a table. They use a table. Now, I'm going to switch to a website. I'm going to show you the same example, and then it will be pretty much what all you need to do. And then I'll go back to the slides. So I'll go back. So I'm going to post is calculator.net. I'm going to post the link to this one here to calculate the scores. So here it is. So let me start from the beginning so you see what happens. So once you go there, all you need is give me your raw score. It says 2.8. I typed 2.8 because I tried this before I started this presentation. Give me the mean. By the way, the symbol for the mean is this Greek letter called mu. The mean is 3.2. And give me the standard deviation. By the way, the Greek symbol for standard deviation is called sigma, lowercase sigma, is 0.4. And all you need is just hit calculate. So here it gives you three possibilities. If you want to see the proportion or the percentage of rides that are less than 2.8 hours, then this is the answer, is 0.15866. Percentage-wise is 15.87% if you round it to the nearest hundredth. So 15.87% means, what does it mean? In this example, you have 15.87% of the rides that are less than 2.8 hours. Now, if you're going to see bigger, well, you can say just 100% minus this. So if you're going to see bigger, so the probability, the percentage, the proportion of rides that are lasting more than 2.8 hours is 84.13%. And it gives you more. Look at this website. It's really great. It gives you, well, if you want to get the z-score again, it's 2.8 minus 3.2 divided by 0.4, which is -1. Yeah, and that's give you those pieces of information again. Now here it gives you between your score 2.8 and between the standard, between the mean. If you want to see, well, how many people or what is the proportion or the probability of rides that are lasting between 2.8 hours and 3.2 hours is actually 34.13%. But we don't need this piece of information. We need this. Well, here it is. That's what it is. Now, let me switch back to the slides so we can get this taken care of. So this is what we got, right? So here they rounded it, and they are going to say, here, okay, well, let's do this one here. This is a new one, I'm sorry. So here, what is the percent horse, right? At least three, when you say at least 3.7% means 3.7 and up. So again, what's the standard deviation of this exercise? The standard deviation is 3.2 hours. I'm sorry, standard deviation is 0.4 hours, I'm sorry. The mean is 3.2 hours. Now we would like to know the percentage, the probability of horses lasting more than 3.7 hours. So according to the slides, we can do it the long way. We can get the z-score and go to the table, and the answer is 89.44. Now I'm going to switch back to that website, to the table, and then I'm going to also put a link how to do this using the calculator, 83 TIA 3 of 87. And there are tons of YouTube videos out there. Just put area and the normal curve calculator TI-86 or 87 on YouTube, and you'll find a lot of a lot of good short videos about that. It's pretty straightforward. But as far as our class goes, I highly recommend that you use that website. It's pretty straightforward, very friendly, much better than the calculator. You just enter the data and you hit the button calculate, and it will give you calculations right there. So without having to deal with any syntax things or any, you don't have to mistype something or whatever. So I'll go back to the website. So again, I will go back to the website. I'll refresh things. So the raw score is this time is 3.7. We didn't change. It's the same exercise, same mean, and the same population. Then we're going to calculate. So, and here it gives you more what you need, really. If you want to have the probability or the percentage of rides that are lasting 3.7 hours or more is 0.89435. If you multiply this by 100, you get 89.43% or 44%. And that's what we get in the slides, right? I'm sorry, this is bigger. This is less than. So did I put 3.7? Yeah, so I said something wrong. This is less than. So when it says at least, the probability of at least, I think there's an issue here, because this is the probability of the scores that are less than 3.7. Means the percentage of rides that are 3.7 hours or less is 89.43%. Now, the percentage of rides that are greater than 3.7 is just 10.56 or 57%. So I think the slides, they have an error. I'm going to go back to the slides and find out. So I'm going back to the same here. Let me share the screen. So I'm going to the slides here. Oh, I just misread it. So this is exactly what we had on the website. It says what percent of horseback rides are at least 3.7, and I read this no, actually they gave us both. They gave us both. So here, convert 3.7. If you do it the long way again, convert 3.7 to a z-score, get 1.25. The area to the left, what does mean? The area to the left means less than 3.7. You get 89.44%. Now, the area above the 3.7 is actually 10.56, which is exactly what we got before. Well, now the last situation, what happens if I would like to know the percentage, the proportion, the probability of, let's say, the times of horse rides between, let's say, 2.8 hours and 4.0 hours. So how are we going to do this? So in the last two situations, we had either less than or greater than. This time we have between. Well, I think the best way to do this, if I go back to the website, is what? Let's find the probability that is the probability of the hours, of the times or durations bigger than 2.8. Write it down, and let's find the hours or the probability of the durations that are less than 4.0. Write it down and take the difference between the two, and we are all done. So I'm going to show you this right now. So let's go back to the website. You're going to start fresh. So I'm going to put 4.0 and calculate. So we would like to know the probability that is less than 4. So 0.97. So I'm copying this, Control C. So this is the probability of times that are less than 4.0. Now I'm going to do the probability of times that are bigger than 2.8. So I'm going to just use this and put Control V right here. And I'm going to put minus. I'm using this as a calculator. And then 2.8, I'm having the probability that are bigger than 2.8 is this. Control C. And then I'm going to go to the calculator and put 0.97725 minus 0.84134 and hit enter. And this is, I get a probability of 13.59%. So I have 13.59% of rides, horseback rides, that are lasting between 2.8 hours and 4.0 hours. So let's check the slides and see if we get 13.59%. So I'll stop here and I go back to the slides. And what it is, so here, so what is that example? Between 4, so this is the percent of horseback rides between 2.8 hours and 4.0. First of all, they converted this to a z-score. So the area to the left, when we talk about 4.0, is this one here, is 497. We got that. Why they say below here? The percent below 2.8. No, we don't want to have below 2.8. We would like to have above 2.8. Oh, this is, oh, I see. So we can subtract that. I'm sorry, I messed up a little bit here. Well, I hope I'm gonna redo this one more time. I'm gonna redo this one more time because I felt like I did this wrong. The last example, it's me. I'm gonna connect. I see what I need to do. Give me 1 second. So this is a very innocent error. I'm going to explain to you everything. So I'm just connecting my tablet real quickly here. And then I'm going to share, I'm going to give you an idea of what's going on here. So here it is. I'm sorry. So this is the normal distribution. So very badly drawn normal distribution. So right at the center, we have 0. And we have here 4.0. And we have 2.8. Those are the z-scores. Okay. Now let me see if I change the color. Where's that color? Can I change the color? I saw it. I saw it. Here it is. So we would like to know this area right here. The percentage of this area. Well, this is how we need to do it. First of all, we will do the 4.0 first. This is 4.0. And we are going to compute this area. And that's what we got. That's 97 point something %. So, and then I need to compute the area below 2.8. This is the error I made. I put above 2.8. So this is 2.8. I need to compute this one here. So to get this area here, I'm going to take the big area minus this area here. So I can get this one here. So that's what I did. So if you want to have, now I'm trying to redeem myself here. If you would like to compute the area or the proportion or the percentage between two values, you need to do the z-score. You need to go to that website and get the area that is less than 4.0 and get the area that is less than 2.8 and subtract this from this one here. And that's how you do it. So if I go back to my website again, which is this one here. So I need to go back to the website. So I need to pick this area instead. I'm sorry, this area instead. So I would like to pick the probability of X being less than 2.8 And that's what I need to subtract from that one. And then hit enter. And the answer should be 81.86%. And that's what the website says. I was thinking that, I'm sorry, the slides say. So that's what it is. So we took the probability. So 97.72% minus 15.87%, and we get 81.85%. So the chance or the probability that a horseback ride lasts between 2.8 hours and 4.0 hours is 81.87 or 85%. So again, so that's the area. We get the area of that is less than 4.0. We get the area that is less than 2.8. The mistake I made is greater than 2.8. No, that's a mistake. So if you take this area minus this area, then you left with the area between the two, between 2.8 and 4.0. I hope that this is didn't confuse you, but if please, if there is some confusion, the slightest confusion, let me know. It's really simple, because we're not doing it the long way. If you're not doing it the long way, again, before I remember this long time ago, when we did this in college, we used to use a table, and I don't know if I can find a table to show you right now. I think that website has a table at the bottom. If I can find it, here it is, the table. So if you want to use the table, if you scroll down, this is the table. So it gives you the z-score. What is our z-score? Let's say z-score is 2.8. Where's 2.8? 2.8.